Welcome to this video on OFDM Cyclic Prefix. In this video, we'll explore what the cyclic prefix is and how it helps prevent intersymbol interference. To wrap it up, we'll demonstrate these concepts through a MATLAB simulation. Now let's get started with the first section. In our last presentation on OFDM, we explored how the inverse fast Fourier transform, IFFT, is used to modulate QAM symbols from an OFDM grid. We saw that each OFDM symbol is processed sequentially, generating time-domain waveforms that are then concatenated together to form the final OFDM signal. However, there's one crucial step in the modulation process that we skipped last time. After applying the IFFT, a small portion from the end of the modulated symbol is copied and appended to the beginning, creating what we call the cyclic prefix. These two steps, IFFT processing and cyclic prefix addition, are then repeated for each OFDM symbol, just as we discussed before. And that brings up an important question. Why is the cyclic prefix needed? The key reason is to prevent intersymbol interference, ISI. Let me show you how this works with an example. Imagine we have two OFDM symbols to transmit over a wireless channel. If we assume the channel is perfect, with no interference or distortion, the signal we receive would be exactly the same as the one sent. However, when the signal is transmitted through the air, multipath propagation comes into play. This means that the signal travels along multiple paths to the receiver. The second path, being longer than the line of sight path, causes the copy of the signal to arrive at the receiver with less strength and a time delay. When the original line of sight signal is combined with a delayed copy within the same symbol, it results in a small change in amplitude and phase, visible in the QAM constellation. However, the end of the delayed copy from the first symbol interferes also with the beginning of the second symbol. This unwanted effect can distort the signal and lead to errors in bit detection. Now let's analyze the same example, but this time with the addition of a cyclic prefix. Once again, when transmitted through an ideal channel, the received symbols remain unchanged. We still observe the delayed copy arriving via the second path. However, this time, the interference from the first symbol affects only the cyclic prefix of the second symbol, preventing it from distorting the actual data. And this brings us to the fundamental principle of OFDM reception. As shown in the slide, the receiver first removes the cyclic prefix from the time domain signal, then applies the FFT operation, as explained in the previous video. This process is repeated for each received OFDM symbol. Now let's move on to the next section, where we'll apply these principles in practice. You can also find the code linked in the description. We start by clearing the workspace and closing any open plots. Next, we define key parameters, beginning with a number of subcarriers and symbols, which determine the OFDM grid size. We then set the cyclic prefix length in samples, initializing it to 0 to first observe the output without a prefix. After that, we specify the subcarrier spacing in Hertz and use it to calculate the sampling frequency. Finally, we define the QAM order, setting it to 4. If you're unfamiliar with these parameters, be sure to check the OFDM grid video where they are explained in detail. Next, we generate the OFDM grid and modulate it using an OFDM modulator. First, we create random QAM symbols as integer values between 0 and 3. Then, we apply QAM modulation to map these symbols onto constellation points. Finally, we use the OFDM modulator, which employs the IFFT operation to convert the signal into the time domain. At this stage, we do not add the cyclic prefix. Let's also plot the constellation diagram to visualize the modulated symbols. As shown in the plot, the 4 QAM constellation consists of 4 distinct points. Now, let's simulate multipath propagation by adding a delayed signal copy with lower energy, offset by 10 samples. Next, we demodulate the signal using the OFDM demodulator function and plot the received constellation. As shown in the plot, the QAM constellation points are distorted due to the presence of intersymbol interference. In the final part, we calculate the symbol error rate. We begin by demodulating the QAM symbols, then compare the transmitted and received symbols to count the errors. Finally, we compute and display the symbol error rate. As shown in the console, the symbol error rate is greater than 0, indicating that errors occurred during transmission. Now, let's add a 12-sample cyclic prefix to the signal. Since this is greater than the 10-sample delay of the multipath copy, it should effectively prevent intersymbol interference. As shown in the plot, the QAM constellation is no longer distorted, and the symbol error rate is now 0. And that's it for this video. I hope it gave you a clear understanding of the OFDM cyclic prefix and its role in preventing intersymbol interference. If you have any questions, drop them in the comments below. You can also find the MATLAB code in the description. If you enjoyed this video, don't forget to like, subscribe, and stay tuned for more signal processing content. Thanks for watching, and I'll see you in the next one.